Example 25 on pipe friction in turbulent flow. This is the last example. The difference in water surface elevations between two reservoirs is 5 meters, and the length of galvanized iron, where absolute roughness is 0.15 mm, between them is 300 meters. Determine the size of pipe needed for a discharge of 240 liters per second. Neglect minor losses and use kinematic viscosity of 1.000 times 10 to the negative 6 square meter per second for water. So again, if you have two reservoirs, the difference in elevation, if you write the energy equation, is automatic, the head loss in the system, neglecting the minor losses. So velocity is 4 times discharge over pi diameter square. The discharge is 240 liters per second, so 0.24 over pi d square. So it is 0.3056 over d square. Then the Reynolds number is diameter. Head loss is FL over d, velocity head. So 5 equals friction factor. Length is 300 over diameter d. 0.3056 over d square, the velocity quantity square, over 2g 19.62. So again, let's set up F over diameter to the fifth. D square times D is D to the fifth. D square is D to the fourth times D is D to the fifth. So we have F over D to the fifth. 5 times 19.62 divided by quantity 300 times 0.3056 square equals F over D to the fifth. So 3.5014 equals F over D to the fifth. Extracting square root so that you have square root of F. So square root of F is 1.871 D to the 2.5. Then the Reynolds number is diameter times mean velocity 0.3056 over D square over kinematic viscosity 1.00 times 10 to the negative 6. So Reynolds number is 305,600 over D. Then let's assume smooth pipe. 1 over square root of F equals 2 log of RE square root of F over 2.51. So 1 over 1.871 D to the 2.5 equals 2 log of Reynolds number 305,600 over D times 1.871 D to the 2.5, that's square root of F over 2.51. So let's simplify first this quantity here. 1 over 1.871 d to the 2.5 equals 2 log of 227,799.84 d to the 1.5. d to the 2.5 over d is d to the 1.5. So using the high-tech calculator, solving for d is 0.320 meter. Then from here, we can solve for f, which is 3.5014 diameter to the fifth. So 3.5014 times 0.32 to the fifth. So friction factor is 0.01175. Next, the Reynolds number, 305,600 over 0.32. So 955,000. Then check the nominal thickness of viscous sublayer if our assumption is correct or not. So 14.14 times diameter 320 mm over 955,000 square root of 0.01175. And it is equal to 0.04371 mm, which is less than the absolute roughness but greater than 0.15, greater than E over 14. So it means that our assumption is wrong and the pipe behaves as the pipe is in the transitional region. So we must recompute F based on the transitionally rough pipe, which is 1 over square root of F equals negative 2 log of E over 3.7D plus 2.51 over RE square root of F. So that's the equation. So substitute. Take note that D here is in meter and E here is mm. So we must divide E 0.15 by 1000 to be consistent with D here because D is in meter here. So 1 over 1.871 D to the 2.5 equals negative 2 log 0.15 over 1000 to make it meter over 3.7D because D is in meter, plus 2.51 over Reynolds number 305,600 over D times square root of F, which is 1.871 D to the 2.5. Let's simplify these terms first in the log inside the parentheses. So 1 over 1.871 d to the 2.5 equals negative 2 log of 3 over 74,000 d plus 4.39 times 10 to the negative 6 over d to the 1.5. That's the simplification. 2.51 over 305,600 divided by 1.71 is 4.390 times 10 to the negative 6 over d to the 1.5. D to the 2.5 over d is d to the 1.5. So using the high-tech calculator again, it's not difficult to iterate d or find the value of d. So d is 0.3438 meter. Then let's compute friction factor based on this new d. F is 3.5014, diameter 0.3438 to the fifth. So it is 0.01682. And Reynolds number 305,600 over 0.3438. So 888889. Then compute thickness of viscous sublayer 14.14 times 343.8 mm over 888889 square root of 0.01682, and that is equal to 0.04217. So it doesn't change much from this value here, and it is still less than 0.15 and greater than 0.15 over 14. So the assumption now that it is in the transition zone is correct. Therefore, the final answer for the diameter is 343.8 mm, and let's make that 344 mm. So I hope that you are able to follow the solution. So for these problems here, it's a matter of assuming first. You may assume smooth pipe, then you always check if the assumption is correct by computing the nominal thickness of the viscous sublayer, compare it with E. If it is greater than E, then the pipe is smooth. If it is less than E over 14, the pipe behaves as fully rough. But if the thickness of viscous sublayer is between E over 14 and E, then it is in the transitional zone. So that's it. And remember, this is the last example.